All right, the recording is started. What we'll do today is to continue our discussion with parameters, local variables, return values, and so on. Um, so that's going to be the focus of today's lecture and also the concept of a call frame. So everything that we are now talking about really has to do with, or they're all based on the caller callee agreement. Now there are some additional documents, that talk about the parameters and local variables, but they're all consistent. Okay, so if you look into the caller callee agreement, that is basically what we are doing at this point. If you have not read it, I highly recommend that you start reading it. You can also upload it to Gemini, okay, make a gem, and kind of use that to help you understand the concepts. Um, Parameters and local variables, this particular module is helpful. It is consistent with your caller callee agreement. All right, so we're going to get started with a sample program, and we'll get it to work in C++ or C first, and then we'll translate that into assembly. So this is going to be how the class goes, for, a lot of, basically for the rest of the class, or for the rest of the semester. So you kind of have to adjust your study strategy accordingly and use the resources that are all available to you. The first one is setting up the tools to help you understand the concepts and to basically perform your own experiments so that you can confirm your understanding. That is mostly in this particular module called Tracing TTP ASM Code Execution. So let me just kind of start with this first, okay? Because I do want you to kind of understand, what concepts you need to understand or what tools are available to you. So this particular module is all about the tool. I recommend that you read the whole thing, okay? Because it is not my job to read my own writing in a class. So I write it so that you can read it, okay? So definitely kind of skip the longer way if you don't really want to, do the long way and go to the shorter way. So in the shorter way, there are, a lot of resources already. There's a video for you to watch. If you're using Windows, there are specific instructions for that. If you are using Mac OS, you only have to watch a portion of the video. You can start at a 10-minute mark instead of watching the entire thing. So it's a little bit more complicated in Windows than it is in Mac OS, but I cannot debug the Mac OS script as well as Windows because I don't have a Mac myself. So if you're using a Mac and somehow you cannot get it to work, definitely talk to me, during the lab time so I can kind of come over and see what is going on so I can make a fix and make that fix available to the whole class. The Windows version should be working as it is described in the video. Okay, so that's basically what you need to do in order to set up Reefer Spider. If you're using Linux, it should be pretty close to the Mac OS version. Everything should work out of the box because I am using Linux myself, so that's the version that gets the most debugging. So with that said, we are going to start with, oh, one more thing. On Thursday, I will talk about the exam from the previous semester, which means your exam is going to be next Thursday. So make sure that you kind of mark it on your calendar. Next Thursday is your exam two for this class. But I will basically give you the exam from the previous semester so that you know how questions are asked, um, last semester. So exam two from spring 2025. See attached. Okay, and I will add the attachment. There we go. All right. So the scope of the second exam is going to include floating point number representation, okay, because that was not in our first exam. It will include the processor architecture, so you have to kind of be able to identify the pathways, how things connect from one component to another component. That would be the kind of stuff that we have already talked about in the lecture quite a few times, okay, when I explain how a specific instruction executes or how it is implemented. Um, and then there'll be one question on PDNC. Okay, so I'll give you a circuit to analyze, and I'll ask, okay, if I change this input from a 0 to a 1, what is going to happen? If I change the other input from a 1 back to a 0, what is going to happen? And so on. So there will be a question like that too. So that is essentially the scope of exam 2. You will not be asked to write code in TTP ASM in the second exam because I want to keep all that good stuff for the final exam. All right. And if anyone is interested, I can always give you, a copy of the final exam from last semester, even now. Okay. Except, we really have not talked about enough topics to really get, to get that covered. Yes. Have a copy of the final exam from last semester. So I might as well do it now. Okay. Because, if I don't do it, I'm gonna forget. So let me send that to you too. Okay, so add another announcement. This is a final exam from spring 2025. See attached. And here we go with the attachment. fx-000.pdf. There we go. And publish. There we go. Okay. All right. So with that said, we are moving on to kind of cover the main topics of today's lecture. Um, and I will be using, okay, let me close the tabs that I really don't need anymore. So this way I don't get confused. I don't confuse myself. Okay, so let me close all those tabs. And then we will continue with the sample program. All right. So I'm going to write a program that illustrates a few concepts. I want something that can illustrate parameters. I want something that can illustrate um, local variables and also return values. Okay, so all of those concepts I want to illustrate. Um, and I don't want it to be overly complicated either. So we'll start with something that is relatively simple, okay? And it does not have, it has local variables, but in two different functions. So it's not one single function, but I think it will suffice. And I'll call this, sigma.c. So we'll start with the C version of the code. So the C version is going to pound include standard integer.h, just so that I have access to uint8 underscore t as a type definition. And the function, I'll just call it f. It takes one single parameter. I'll call it n. And we'll kind of use the conditional statement approach instead of the ternary expression approach, just so that it's easier to refer to which part that we are talking about. So we'll say if n, then we do this, else we do that. So if n, which means n is non-zero, we are going to go for a recursive call. So it's going to return whatever n is plus the result of f of n minus 1. Otherwise, it just returns n itself, which is basically a 0. So that's f, function f itself. Do we have any questions about function f? Okay. How many people have some kind of exposure to recursion? Because that's what this is. It's a function calling itself, that's recursion. Um, the most, um, the interesting thing about recursion is it is difficult in some people's mind because they overthink it. In this class, we are not going to overthink it. We'll just go like, okay, what do we do when we call a function? What do we do when the function returns? What do we do as the function being called, okay, to access the parameters? Nothing changes just because it is recursive. The real difficulty of writing recursion is the construction, the design of the function itself, but you're not asked to do that in this class. Okay, in this class, you're always given the C code, and your job is to translate the C code into assembly code. So the focus is a little bit different. But the way we debug the program is going to be, that can also get a little bit challenging. So we'll go, take a look at that later on. Main has a local variable, let's call it x. X is going to get, f of 3. Okay, this is what I really want to do, and return 0. All right. So just from the way function f is defined, can somebody tell me what is the result of f of 3? So you can use a piece of paper to help you, okay? You can also use, because I think looking at it is not easy, but if you have a piece of paper, it gets a little bit easier. So you look at f of 3 and you ask, okay, f of 3 is going to be 3 plus f of 2. F of 2 is going to be 2 plus f of 1. F of 1 is going to be 1 plus f of 0. F of 0 finally is going to be 0. So when you unfold the recursion, then you end up with 3 plus 2 plus 1 plus 0, which is 6. Yep, so that's what it's supposed to be. But I don't take chances. Okay, so we will go ahead and kind of get this program to compile and run in GCC. And then we will move forward to the assembly version of this. So GDB Sigma, okay, list the program, put a breakpoint on line 14, run the code, and we just look at x. X is indeed 6, so the function works the way it's supposed to. Okay, so now we are ready to translate the program into assembly language. So cp sigma dot c to sigma dot ttp-asm, and now we can just go ahead and edit the ttp-asm version. So first thing first, introduce comments so that everything is commented out. There we go. And now we can do the usual. This is the entry code. The entry code is, there's a parallel to the entry code in a normal C program on a normal computer. There's a little bit of snippet of code that runs before main function gets control. Okay, so that entry code is what is supplying the arguments. When you type a command on the command line, you can supply, like, what we call switches and other parameters. They get passed to two specific parameters of main that we usually do not talk about in the class. Okay, so that entry code, this entry code here, is kind of doing that type of entry code in an actual environment, except in this case, it is very low level. So all we want to do is to, let's just say that we want to initialize the stack pointer, and then we are going to um, specify the return address, um, push it on the stack, and then do a JMPI to main, which we'll define later on. And when main returns, we just get to the halt instruction. So I did, kind of verbally describe what each line is doing, and I intentionally did not type the comments in, okay? Because, I think I might have said this several times already. I want it to be an exercise for you guys to do, okay? Because the way I explain something may not be the way that you want to write down the explanation. So you want to write it down the way that you would understand instead of the way that I would describe it. All right, so we get to main, okay? So we get to main right here. And the way I usually do things is to specify the return code of a function right away. So that would be LDD BD, increment D, and then JMPB, all right? So that's the usual sequence that I choose to use when I'm ready to return from a function. But in the final exam, I may choose to use a sequence that is different, okay? In other words, you need to understand what each line is really doing, okay, from line 24 to line 26, so that if I use a different way to perform exactly the same function, you can still recognize it, okay? So this class is not about rote learning, it is about understanding what is happening on the stack in the context, in this case, of a C program. All right, so I have a minimalist program right now, and I'm going to test it right away. And this is why you probably want to install River Spider, because it does give you the ability to do this, when you are writing your own, functions and doing your own programming assignment, which we'll have soon. Okay, I know many of you are kind of waiting for that to happen, so you'll get the chance to kind of do that. So we go to River Spider, and then we just click type submit, and then sorry, I got distracted by a seagull that kind of flew past the window. Um, yeah, just because we don't have squirrels, up here, does not mean I don't get distracted. Um, all right, so it is called sigma.ttpasm. So this is all you need to do. Once you have the tool installed, this is all you need to do in order to get it to assemble, run in the simulator, and then look at the trace. Without this, I can show you how you can do it. Without this tool installed, you may not like it. Okay, so this is the minimalist program. We have the no op initialize the stack pointer, and we can see the stack pointer got initialized. This is the return address. Okay, it is at location 9. We decrement the stack pointer and then store whatever register A has to wherever the stack pointer is pointing to. So that's what this particular cell is reflecting. We are writing to RAM. Location FF is now changed to 09. And then we do a JMPI to main. This is the main, but main doesn't have anything to do. It returns right away. It pops the return address into register B, increment the stack pointer because that's part of the pop operation is to deallocate the location that we just retrieved content from. So the stack pointer got back to location DD, and then we do a JMPB, which continues execution based on whatever register B has. So it continues execution at location 09, which is reflected here as well. And we get to the halt instruction that marks the end of the current program. So are we good with this trace? Are we understanding how to read the various columns of the trace? So we're good? Because this is really crucial. Okay, if you have a question about how to read the trace, now would be a good time to ask. Because if you don't ask a question, since I'm not a mind reader, I'm going to have to assume that you know what each column is representing. All right. I should probably have a little watch, timer. Okay. So every time I ask a question, it will give me like a 20-second, timeout. So I would just kind of wait until it times out or when somebody actually has a question. So we all good? All right, cool. All right, so now we go back to the code. So if I were using get, in order to maintain versions of my program, I would check it in now. I would do a commit, okay? Just so that I have a baseline of, okay, this program is minimalist. It doesn't do a single thing. I don't even have the local variables allocated, but it works, okay? It works in the sense of I can call main returns. So this way I have a baseline. If later on I somehow messed up and main does not even return back to the halt instruction, then I can go back and say, okay, what did I change to mess up the program? So I would definitely use, get, as a utility program. Git, is the name of the command line program that inspires, GitHub, and also I think that's another website for using Get. What is it? GitLab. Thank you. So GitLab and GitHub are both based on the utility program called Git, Git. All right, so now we can go back and now say, okay, I want main to allocate the local variable x. Okay, so the way I do it is, I would allocate local variables from offset 0 of the frame. So we'll talk about the frame, in just a moment. We'll visualize the frame. So all the local variables are at the lowest portion of a frame, followed by the return address, and then followed by any um, parameters if there are parameters. So this is the lowest one because it's the only local variable. And then I always use LVS to indicate the number of bytes that I need for local variable size. That's why it is called LVS. I used to spell out the whole thing. So in the lab, you might see local bar size. It's the same thing as LVS. Okay, I just decided, why type so many characters when I don't have to? So the way it is computed is the offset to the last local variable plus the size of the last local variable. So that one plus is uh, adding the number of bytes that we need for the last local variable declared. Okay, and that's kind of all I need here for main. So the first thing I need to do by line 20 and 21 only define the labels. It has no runtime behavior whatsoever. In other words, if I were to run this program right now, it would behave exactly the same as before. Okay, because the label definition does not change runtime behavior. All it does is to tell the assembler, oh, when you see main X, it is a 0. When you see main LVS, it is a 1. That's all it does. Okay, it does not generate any app opcode whatsoever. But the allocation of the space for local variable is a runtime thing because until you call or invoke a function, you don't need that space on the stack. So that's why the allocation and deallocation are both runtime behavior. So that means we need instructions to do it. So we do a LDIB main LVS, and then we subtract that much from the stack pointer to allocate. And then when we are ready to return, we also have to remember to deallocate before we try to retrieve the return address, because otherwise the stack pointer will be pointing to the lowest local variable instead of the return address. All right, so I have allocated, I have deallocated. So now what we will do is to run this code, which doesn't really do anything, but we're going to run it anyway because we want to find out what is happening to the stack pointer, and then we can also try to draw a picture of the call frame for main. All right, so make sure I save the code. Let's see. Nope, I did not. Now it is saved. Run the program again, and I'm going to start a new document uh, in the folder. Let's see here. So I want to start it in a folder that you guys can all see. So that would be shared. There we go. And make a Google Sheets out of it. So this particular Google Sheet is going to show you a picture of what the stack looks like and what the frames look like, in relation to each other. So 2025, 1104, and start with location 255. That's the highest location in memory. And then we are going to go this cell -1. So this way I don't have to type all those numbers. Okay. So we just kind of drag it down to here. I don't think we need that many locations, but just in case. And then we have dec to hex for base conversion, because the most of my tools work with hexadecimal numbers, so it's good to have the hexadecimal as well as the decimal numbers available. This makes it a little bit easier to read. Column C, I'm going to use it for the actual content, at those locations, and I would use column D to indicate what is the purpose of that location. So this would be the return address to the entry code from main. That's what we pushed. And from what we could see, it is pushing a 09 on the stack, at that point. And then the next location is allocated for local variable x of main, but we only allocated the location. We really do not know what is the content of that location. So when we are in the middle of main, this is where the stack pointer should be pointing to, before the deallocation. So we're going to go take a look at the trace itself and see if it is consistent with this. All right, so right after JMP I to main, we subtract that much from the stack pointer. So right after this, this is where the stack pointer is pointing to. It is pointing to location FE, and if we look at the stack picture, it is in fact pointing to the location FE when we are quote unquote in the middle of main, after the allocation and then before the deallocation. So are we doing this okay? All right, at this point, okay. So when this is all done, you can take a snapshot of the assembler just by going to um, well, you can take snapshots of all of the things, okay? Everything that you see on the projector, you have access to already. You have read access, which means at any point that you want to, you can basically just save a copy right at that point, and that, you basically freeze the document at that point, and then at a later point, you go like, okay, I want another snapshot, just do it again, okay? So these are the resources that are available to you, and I would try to kind of recommend how to use the resources. All right. So it looks like the program worked just fine. Okay, the stack pointer is back to 0, 0, which means the stack is balanced. By the time we get back to the halt instruction, that marks the end of the execution of the program. So I have no reason to doubt that the program is problematic at this point. So we're going to go continue with the coding. So the coding is now saying, okay, we got this done. Okay, we got our local variable. So now we want to change x to the return value of f of 3. So instead of calling f of 3, I'm just going to put a specific value. Okay, so this is a to do. Okay, remove this test code because I want to see if I can just overwrite local variable x of main with just a particular value. So let's just say that we want to assign 42 to x, like so. So now I put the 42 into register A, and then I try to calculate the address of x. So the first thing we need is the offset to x from where the stack pointer points to. That's what the label main x is representing. And then once I add the stack pointer to the offset from where the stack pointer points to x, I will end up with the address of x, and then I can store register A to wherever register B is pointing to. So that should do the trick. Okay, so I'm gonna save this code and just run it. Okay, but before I run it, I want to go back to my picture and go like, okay, so given this is the program that I have right now, I think the 42 in decimal should be stored here. 42 in decimal is 2a in hexadecimal because it is 2 times 16, which is 32, plus the a, which is a 10. So that would make a 42 in base 10. So this is what I expect the program should do when we are in the middle, right after the assignment operation. So with this prediction, I can now go back to the code and just test run it. So this is the kind of exercise, okay, that I think you guys need to do when you are given a programming assignment, okay? It's not to write the code from the beginning to the end in one single shot, okay, but to write it in very small steps. And then between the steps, you test it, okay? So now we get back to the trace, okay, in the assembler, and then we go like, okay, did we write the 2A to location FE? Yes, we did. Okay, so this is a verification that what I expected the program to do did happen. And then I also always double check that we get to the correct halt instruction. And by the time we get there, the stack pointer is balanced. So those are the things that I always double check when I test run the program. Do we have any questions about the process of writing the program? You all good so far? All right. Question? Oh, we're good. Okay. All right. So now we can, turn our focus to the function f. Okay. So we'll go ahead and, kind of go back to function f now and try to implement the function. So f colon is really just the entry point. But since we do have one parameter, I kind of need to know how to get to the parameter. We can do f LVS as a 0 because there are no local variables. If there are no local variables, naturally you do not have any um, LVS would be 0. And then we try to calculate the offset to parameter n. That is always f LVS 1 plus. So even if we have local variables, it would only change how we define f underscore LVS, but it would not change the relative position of the last local variable versus the first parameter. That will never change. Okay. The 1 plus here, this one has to do with the return address. Because once we have all the local variables allocated, then we have the return address, and then on top of the return address would be all the parameters. Now that order has to do with the caller is responsible to push all the arguments first. So the arguments would be pushed in this order on the stack, and then the last thing that the caller push would be the return address. And that's why the return address is sitting at the bottom of everything that the caller is pushing on the stack. The callee, on the other hand, takes control after the return address was pushed on the stack. So that's why all the local variables are below the return address. So is that okay so far? Kind of. I will show you the picture too. Okay. So now I know how to get back to local variable n. I will also do the return at the end. So we have the LD, BD, increment D, JMPB at the very end. So right now the function f is all done. It doesn't do a single thing. Okay. So what I can now do is to just kind of check out what is happening, when we get to the middle of the function f. So I'm going to put the halt instruction right here. Okay. So it's right at the entry point of f. And then in main, I'm going to say, okay, let's not do this silly thing. And we're going to actually call f with an argument of 3. So we push arguments in a reverse order, which in this case really doesn't matter because there's only one. So we push the 3 on the stack. So that's how we do this. LDI A3, decrement D, and then we do STDA. Now, in many Cisp architecture, all you have to do is to say push, and then there's usually a special symbol to mean an immediate operand. So this is what you do on a Cisp architecture. Line 36, one line, one instruction is going to do what we need 3 lines to do. Okay, so the 3 lines, line 33 to line 35, is what a really RISC processor would do because each instruction cannot really do much. But on the CISC architecture, the 3 instructions from line 33 to line 35 combine to just a single instruction, which is line 36. But the reason why I don't do that, okay, I could have implemented something like this, but I decided not to because I need to kind of make sure that you guys know how the stack is utilized and not just know that, oh, there's a push and there's a pop, there's a call and there's a return. They kind of have to match up, with each other, but you would not end up actually understanding how things are actually happening on the stack. So I just boil everything down to the most basic instructions possible. All right, so we push the argument on the stack. Once again, when you get this document or when you get this source code, you want to document and comment each and every single line, okay, of why it is there, what does it do, and how does it relate to the C program. Okay, the most important part is how does it relate to the C program. So this is the return address. Now we push it on the stack. And then we can now do a JMPI to the function, which is f. When the function returns the argument of 3 is still sitting on the stack, it is not useful anymore, but I don't need to pop it into anything. All I need is to deallocate it. So I can do the increment D without the LD instruction in front of it or ahead of it because I don't really care about the value. I know what it is, and it is not of any value to me at that point. So I don't need the LD instruction. I just need the increment D to deallocate it on the stack. All right, so I think this program should operate, okay? It will never get to line 40 because I put a halt instruction in the function main, sorry, in function F. So it should get to this halt instruction and stop right there, okay? And the purpose of doing this is I want to visualize what is on the stack and be able to tell, okay, these bytes belong to the call frame of main, these 2 bytes belong to the call frame of F or the first invocation of F. So that's the purpose of this particular test run. Once again, make sure the code is saved and then go run it. Oh, okay. Oh, let me run this without River Spider just to give you guys some incentive to get it installed. Okay. Do you guys want me to kind of do it the long way, which I have been doing for years before I wrote River Spider? Okay. So it's not like it cannot be done. It's just tedious. Okay. So we'll do it the tedious way. The tedious way is to get the program into the clipboard. I do it on the command line, but you just kind of Control A in Notepad, Control C. Okay, that's all you need to do. But to me, this is what I need to do. X clip dash cell clip redirect file name like so. So now it's in the clipboard. Switch to the assembler. Go make sure that I go to um, the correct tab. Okay, maximize. Go to the source tab. Erase. I typically erase the whole column first. Okay, but you can do it any way you want, and then paste it in. Wait until the loading or the error is all gone. Takes a little bit of time. Okay, so done. All right, making sure that is the case. Go to RAM file, go to file, go to download, CSV, specify the location, and I typically just use exactly the same file name with a different extension just so that it's easier for me to identify what RAM content I'm saving. Okay, save it, replace it because it's already there because of River Spider. Switch back to the command line. And now I need a really long command to run Logisim on the in the command line mode. So this is the way that we do it. Java-jar, and then you have to locate the folder or the path of where Logisim 310 is located. So in mine, it is a little bit long. Okay, Logisim 310. Okay, so this will start Logisim. Okay, if I were to press the enter key right now, it just launches Logisim in graphic mode, which is not what I need. So what I need is to also load the processor 0004.circ circuit. So it's the location is the same place, okay, processor and processor 0004.circ. So if I were to press the enter key right now, it would launch Logisim in graphics, graphical user interface GUI mode with the processor preloaded, okay, but not the RAM file. Okay, so I also need to load the RAM file, which is a dash load. So now I need to specify where I saved the CSV file, which is sigma.csv. Okay, so now it's going to preload the RAM with the downloaded RAM content. So the program is ready to go. Then I have to specify -tty table so that the output in a specific format. And okay, so press the enter key. This is what it generates, but it's on the display or standard output, which is not really useful. So I have to capture this to a different file. So I typically capture it to a file with the same file name, sigma.tsv, because it is tab separated value. So now I have the TSV file generated. Then I have to switch back to the assembler. I have to go to the raw trace raw data tab, go to file, go to import, and then remember to upload the file first. Okay, so the upload part is the easy part. So I just have to go to my temp folder, go to sigma.tsv, not CSV. Okay, upload it, and then not to create a new spreadsheet, but to replace current sheet. Okay, so click that. This is a TSV. We know that already, so don't even try to detect automatically. And most importantly, do not convert text to numbers, dates, and formulae because the script will automatically do that. Click import data. Then you can switch back to analysis, and we have essentially the same thing with a lot of empty rows because they're not pruned or trimmed as with the other approach, but it does get everything done. So would you rather be doing this or just type the up arrow key and then press the enter key? The choice is yours. Choose wisely, as they say. Yes, I can hear the Indiana Jones, theme music in my head right now. All right. So that's how we do it, without using River Spider. Yes, it can be done. I have been doing this for years. Okay. And then one day I just decided, okay, I guess it's time to write a script to do the same thing, mostly as a technical challenge to myself because I just like to solve problems, okay, make things work a little smoother. So let's go back and do this in using River Spider instead. Okay, so to do it in River Spider, that's all you need to do. So the setup of River Spider does take a little bit of time, especially the first time that you do it, but I think it's well worth it. Well worth the time because it just gives you a much more concise output. It's the same thing, it's just a whole lot more concise. All right, so getting back to what I wanted to demonstrate is what is the lowest point of the stack pointer. So all you need to do is to track the stack pointer. Okay, every time we change it, you just go like, okay, making a note, it keeps getting lower and lower. So this is the lowest point. And then you also keep track of what is on the stack. The 03, which is our parameter n of f, is at location fd, and this is the return address from function f back to main. So now we get back to this map here and we go like, oh, okay, we know what's happening here. There's a 03 here, which is the parameter n of function f. And then over here, we have the return address from f to main. And let me just check what it is. It is supposed to be 1b for this particular version of the program because that does change over time. So we'll just kind of type in 1b, and this is the return address from f to main. And the stack pointer is no longer pointing here. We are now having the stack pointer to point to here. So is that okay so far? We have two call frames right now. Okay, we have two frames. The first frame belongs to main. The frame that belongs to main would be these two locations. So I'm going to color code it. Um, let's see. So this is one frame, which provides the context for main. And main only has a local variable, which is really needed, but it also needs the return address to go back to the entry code. The next two locations belong to the first invocation of f, which implies there will be more invocations of f later on. So we're going to color code it too. Okay, so this is the call frame of the first invocation of f, and in that particular context, once we also have the return address, but we also have parameter n of f sitting at this location, which is exactly 1 byte on top of the return address. Are we doing okay so far? All right, cool. All right. So you have to remember the base of a frame is the lowest location of the entire chunk of memory. So that means the base of the frame that belongs to main is here. The base of the frame that belongs to the first invocation of f is here. Okay, so you have to kind of keep track of what is the base of the frame. All right, so it looks like everything is working correctly. Okay, so now we go back to the code and we try to implement the rest of function f. So take that out. So now we have a conditional statement. We want to see if n is non-zero. So that means we have to retrieve n first. So we need a LDI b. I'll make it. B is fine. Well, LDIB with f underscore n, that's the offset from where the stack pointer points to n. Now, technically speaking, it is where the base of this is the relative offset from the base of the frame to parameter n. But since the stack pointer is pointing to the base of the frame, so we also can call this the offset from where the stack pointer points to parameter n. So to get the actual address, we have to add the stack pointer to the offset so that we get the address of n. And then we have to do a LD in order to get to the value of n. And then we can do an AND BB to kind of push it through the ALU and therefore affecting the Z flag along with the S flag. We don't care about the S flag in this case. We only care about the Z flag. And then we do a JZI and go like, okay, if it is 0, where do we go? So the way I do it is, to follow the compiling convention. If the condition is false, we get to the else branch, and then otherwise we continue with the then branch. So we go to else 0, and then whatever is here is going to be the then branch. And at the end of the then branch, we also need an unconditional branch to the end of the conditional statement. So now, excuse me, now I need to also define the else a label to be here, and also to define the um, and if label to be here. So that ends the entire thing. So that's the structure of a conditional statement. And if you're asking how can I possibly know, what to do with constructing the conditional statement framework, that's in, okay, I'm going to point out which module. So, oh, it's on the other side. There we go. So that particular module is compiling C control structures. Okay, so make sure that you know where to find that information. So now we can continue with this code here. All right. So at this point, okay, I'm just gonna test the code again. In other words, I'm gonna pass 3 to F, make sure I end up in the correct branch, and I'm gonna pass 0 to F to also make sure I end up in the correct branch. Because otherwise, I can be adding additional code and it will all be wrong because this part is wrong. So I'm going to test the code now, and the best way to test it is just to put a halt instruction here and put another halt instruction, not here, sorry, put another one right after the conditional branch, which is here. And one trick that you can also do is to comment your halt. So this is an indicator that we are in the then branch. And then this one is an indicator that we are in the else branch. Indicator that we are in the else branch. All right. So the reason why it is useful to put comments after the halt instruction is the trace would show the entire line. So that means it would show the halt instruction, but it's going to show the entire line, including the comments. So that means I don't have to go back and forth between the source code to try to figure out, okay, we have 2 halt instructions, 3 halt instructions here. Which one did we go to? It would automatically tell us which one we got to. So by that token, it might be a good idea to also comment this halt instruction here. Okay, this is the final halt instruction, and it marks the end of the program. Okay, so now all 3 halt instructions have their own comments, so it's pretty easy to read in the trace. Save the code again, run it again. So you can kind of imagine without a Refer Spider, what I need to do in-class demonstration is a little bit more time consuming. But now it's like that. There we go. Go back to our assembler, okay? And since we are fairly sure the program is already working up to a certain point, we just get to the last one. We get to this halt instruction, and it says we're in the then branch. Okay, that is correct. Okay, we're supposed to be in the then branch because we passed a 3 to function f. So now I go back to the program and pass a 0 instead. So go back here, go to the part where we push a 3 and we change it to a 0. But I'm going to remind myself, change this back to 3 after testing. Okay, so every time I change my code, just because I wanted to test a little bit of something, I'm going to remind myself to change it back. The other way to do this is even to comment out the original line of code, add a new line of code, and then put a to do to remind yourself. Some editors automatically would highlight the word to do as one single word, all uppercase, and others do not. This is Vim and it's very programmable. So I personally like to have to do highlighted. So that's a personal preference kind of thing. So now we test run the program again. This time it should end in the else branch. So we want to make sure that that really is the case. And it does indicate that we are in the else branch this time. So that means the conditional statement is working, or at least we have we have some pretty good evidence that the conditional statement is working properly. Do we have any questions at this point? No questions? All right. So I do have to remind everybody that I it is not uncommon that I have heard people saying that when you are talking, I understand everything 100%. The moment I walk out of the classroom, I think I don't understand anything anymore. It is not uncommon. The reason why that is the case is because your short-term memory is actually, guess what? Short-term, as in 30 seconds. So you can maintain the cognitive context to understand everything that I'm talking when you're actively engaging in the material. The moment you walk out of the classroom, you're thinking about your next class, what you're going to have for lunch, who pissed you off today, and so on and so forth. And everything just whoof, evaporates. So unless you write it down and kind of try your best to incorporate it into your long-term memory through understanding, through the logical connection, it is not, it's difficult to recall what I teach in the class. Okay, so I just want to kind of give you guys a little bit of the background of why we take notes and what you need to do in order so that you can retrieve that information when you need to in a final exam. All right, so with that said, we are going to move on to the branches. Okay, so one branch is really easy to do. This is the easy one. Okay, the else branch, we have to return a value of 0. So that means we just have to specify a return value of 0. This is one way to do it. Okay, but this is the boring way of doing it. So why do things in a boring way when you can do it in a more exciting way? And it saves 1 byte in RAM, because when you subtract a register from itself and store the result back to itself, what does it actually do? Turn it into a 0. Yep. All right. So now we go back and work on the the then branch, which is the more complicated one. So we'll go ahead and deal with this one here, which is this is the slightly nastier one. Okay. So the way we look at this is, once again, we use dependency-based thinking. In other words, okay, what needs what and so on. The final operation that we want to do is to specify the return value. We want to LDIA with something, okay? That is the result. But the result is an addition, so that means before that, we need an addition. The addition relies on n, which is not a problem. That's my parameter. I know how to get back to it. We need a function call because this we need to add the return value of f of n minus 1 to the value of n. That becomes my own return value. So that's kind of the dependency thing. So I'm going to work on f of n minus 1 first. At this point of time, the value of n is still in register B, so that's kind of handy. I just do a decrement B and then push it on the stack. Okay, decrement D, stda. So line 21 is computing n minus 1 in register B. Lines 22 and 23 is pushing n minus 1 on the stack. And then we proceed to push the return address, LDI, A, B, whatever, C. Okay, they all work here. Um, and then we do a decrement D, stda. That's how we push the return address on the stack. And then we do a JMPI to the function that we are calling. Well, guess what? It turns out to be the same function that we're in. But we are not changing the way that we call a function, the way we push the parameters, the way we push the return address, the way we compute the return address, and also the way that we deallocate the argument after that. None of that is changed just because it is a recursive call. So this is why I said earlier that the difficulty or the challenge of recursive call is because people overthink it. Okay, the mechanism does not change at all. Okay, all right. So this is all done. So by the time we get to this point, register A should have the return value of f of n minus 1. So all I need to do is to add n to register A. So some people will go like, oh, but Tech, you have n already in register B, and all we need is something like this. But since B is already decremented by 1, we just have to kind of make up for that decrement by 1, and this should do it. And the answer is no, we cannot do this. The reason why we cannot do this is because after a function call, you have to assume all registers are modified. They're gone. Okay, whatever they had before, they're gone. Okay, so if anyone is asking, but why? Well, that's because it's part of the agreement. What agreement are we talking about? This agreement that we are talking about, not this one. This one. Not this one. This one. Okay, there we go. So when you read this one, it would say, from the caller side, you scroll down a little bit, and it says the values of registers A, B, and C are not assumed preserved, which means they can be overwritten, they can be preserved, maybe, maybe not. Okay, so do not make assumptions that the register values are preserved after a function call. We good so far? All right. So now we can, I hope you start to understand why this particular document is super duper important. Okay. Because everything that I do is currently derived from the agreement itself. Is that okay? If you have not read the document, it is time to do it. Okay. There's no substitution for reading the material that was intended for you to read, because that's the reason why I wrote it. It is part of how the information of this class is disclosed or distributed. And it is also echoed on the callee side. The callee side also mentions something about the registers. There's no need to preserve the values of registers A, B, and C. So that's another hint of saying, oh, okay, after a function call, I cannot assume the values of a register stays the same. Well, it's okay. It's not a big deal. All we have to do is to recompute it. So we're going to get rid of these and start from scratch. We just have to do LDI. Let's put it into register B. I cannot use register A at this point because register A has the return value from the function call. So LDI B with F underscore N, add BD so I can get to the address of N, LDBB so I get to the value of N. And now we can do add AB. So that's adding the value of n to the return value of f of n minus 1. And the result is automatically in register A, which is exactly where I need it. Save the code. Now, when you're debugging something like this, okay, and I still have this little to-do thing to change, but I'm not going to get rid of the to-do because I'm going to go for the simplest recursive call. F of 0 is not going to do any recursive call because it's supposed to return the 0. So f of 1 is the first one that does a recursion. It will do so now with this particular one, I should have two invocations of f on the stack. The first one using 1 as n, the second one is using 0 as n. So that's what I'm expecting on the stack. And this is what we're going to do is to run it and see if that is the case. So when you're writing recursive functions, always test the base case first. Because if your base case is not working, forget it. The recursive call is not going to work either. Okay? So always test the base case and then give it the simplest recursive case, to test it, and then you give it something that's more complicated. All right, so we're gonna resubmit the job, okay, and make sure that it is saved. Yep, it is. And then we go back to the trace and try to see what happens this time. But before we do that, we go to this picture here and we just go like, okay, according to our new test code, this is one particular frame and this would be the other frame. Okay, we should have 0, 0 over here. This is again end of f of the second invocation. I don't know exactly what is the return address that I should be using here. I can look it up, but this is going to be the return address from f back to f. Okay, so we do okay so far with what we are anticipating to be on the stack with this particular version of the code. So we are all good? Okay. So I'm going to color code this, okay, just so that it stands out, easier to read. And we are just incrementally shifting to the red side of the spectrum like that. It looks nice. Gradient. All right. So now we switch back to the trace and see how we are overwriting RAM locations. So we can see that, okay, so here's the 0, 1, okay, matching this 0, 1 over here at location FD. That is all good. And then we are using the return address has now changed to 33 because as we add more code, the return location does change. So that's okay. It's not a big deal. This is still correct. And then we're expecting a 0, 0 to be stored at location FB. So we just scroll down. We go like, oh, that is not good. Okay, because we forgot to actually push. Okay, so that's this. All right. Well, I'm actually stoked. The program is not working. I'm actually happy because of two things. One is selfish. I like to solve problems. This looks like a problem to be solved. Second is for you. I can now show you how to debug a program, which you'll be doing a lot for the rest of the semester. So it's not working. I'm not getting what I'm expecting to see. What I'm expecting to see is here. So this is the first thing is before you debug a program, you need to know what it is supposed to do. I'm supposed to see a push of 0, 0 at location FB, and instead I'm seeing a different thing. So now we can execute a program backwards. Okay, we start with the symptom. We start with the first symptom that we can identify, which is not exactly where the problem is, but we can try to trace it backwards. With a regular C program, even using GDB and all the other debugging tools, you cannot run a program backwards because it doesn't store everything along the way. With this, you can, okay? Because it has the entire trace with everything that the program did to all the memory locations, to all the registers, to all the flags in the flags register. You can actually execute a program backwards, which is what we're going to do now. Okay, so it is storing the wrong thing into location FB, which means register A is not getting the right value to begin with, and that is from uh, line 23. And on line 23, so we want to figure out what we are supposed to be pushing on the stack. And register A does not seem to have anything stored in it by the time we do it. So I think we pushed the wrong register on the stack. I believe we're supposed to push register B on the stack, and I did a typo of a register A. Okay, because register B has the correct value. It was never pushed on the stack. Okay. And then the return address is actually stored on the stack correctly here. Okay, so this is the correct return address. So my suspicion is we just got the wrong value to store on the stack. So that makes me also doubt whether 33 is the correct return address. So I'm going to double check it. So we go to the assemble tab and then we look up location 33 in column W to find out exactly what location it is. Okay, location 33 is right after the JMPI, so it is in fact the correct return address. What I did wrong was not pushing the correct argument on the stack. So we need to go back to the source code now. Okay, go back to the source code, go back to the line where we were supposed to be pushing the argument in F. So we're supposed to be pushing F minus 1 with decrement B, so it is now N minus 1. But instead of pushing that on the stack, I push register A instead. So I changed this to a B, and I would even leave a note behind was register A, probably an error. Okay. The reason why I leave a note to myself like this is because if I kind of forgot about what register A has, which is significant, and it's supposed to be somewhere else. I know what I changed and the reason why I changed this line. Okay, so once I verify the program is working, then I can get rid of this comment and go like, okay, I fixed the code. This is also why using Get or any type of revision control program is going to be helpful because you can compare between check-ins. Okay, and also, okay, this is also related to your future self. Um, in your first interview, even as an intern, and you can say that, oh, I use Get all the time to do my homework, so I can keep track of the versions and help myself debug the program more effectively. That's a huge, big star on your, you know, in your interview. Okay, if you try to interview for a real job and you say, I don't know what Get is, if they had a bell, they would just slam on the bell repeatedly. It's like, okay, next interviewee, please. Okay, because the employers are now expecting everybody to know the tools they need in order to become effective developers. And Get is kind of like the baseline of those tools. All right, so getting back to this, and we are going to go to the trace. I think I ran it already. Well, I'm not 100% sure. So we'll see. Maybe not. Okay, because it's still the same here. So maybe I have not done that. Okay, save and run it one more time. And you might notice that I don't like to use GUI tools for the most part because using GUI tools takes a lot of control away from me, and when problems happen, I don't really know why it is happening, and takes me more time to find out what is happening. All right, so now it's pushing the 0 here. Ah, we are good. Okay, so we are matching this 0 at location FB, and then the next location would be the return address, whatever it turns out to be. So we can now see, okay, it's location 1A. We can double check to make sure 1A is the return address, the correct one. We go to the assemble tab, and then we just locate 1A over here. Yep, so it is right after a JMPIF instruction, so it is the correct return address. All right, so with that all working, I can now say, okay, I'm just going to go all the way to the end. Am I storing a 0, 1 to local variable x of main? Yep, okay. So going back to the stack picture here, we are now overwriting this location with a 0, 1, okay, which is correct, okay, because f of 1 is giving me a result of 0, 1. And to finish up the checking, I just go to the end. We end up at the correct halt instruction, and the stack pointer is back to 0, 0. So everything checks out for me, okay, with the simplest recursive case of f of 1. So now I can go back to f of 3 and see what happens. Do we have any questions about this process? Because I'm not only illustrating how parameters work, how return values work, how local variables are allocated, how we deal with the stack. I'm also trying to show you guys how to write code in this context. So if you have questions about the technical stuff, which is how the stack is used, it's time to ask. If you have questions about the process itself or how to write code, in this way, which is very incremental, okay, you can also ask questions about that. So do we have any questions? Okay, I don't see any questions. Okay, so I'm not implying anything, but in case, just in case, somebody is thinking, I don't even know where to start asking the question. Now, that is problematic. I would say, for those people, it may be a good time to have a conversation with me before class, okay, during my office hour, so I can help you kind of diagnose, where the misunderstanding or the lack of understanding is, and what strategy you might be able to use for the rest of the semester. There is still enough time, okay, but something might need to be modified in order to get to the end. All right, so we now go back to the source code and change it back to f of 3 in main and see if it is going to return a 6 and store the 6 at the location. But we will also take a look at the stack operation and see whether we see the 3 invocations of f along the way. All right, save the code, run it. So the way we study for this class, okay, is the programming assignment is a good way to study for the class because as you write the programs, you have to remember how to do something, and that is how you kind of let the concepts kind of gel by applying the concepts. So now we go back to we can go back to the trace first and just kind of go straight to the end. And we see that a 6 is in fact stored to location FE, so the program worked the way it is supposed to. But we're going to go one step further, okay? Because I want to know what else is stored on the stack. So that means I'm going to have to track down, all the store operations, related to the stack. And the spreadsheet gives you a pretty good tool to do that too. So you can do a control, I cannot remember, I always go to the edit control H, there we go. So now you can say, I'm looking for um, whatever, star. You can do a regular expression thing. I might as well. I'll show you what to do with a regular expression. So search using regular expression. So that means the star needs to be escaped first, and then you specify two hexadecimal digits. So that means it is from 0 to 9, A to F, and once again 0 to 9, A to F. You can probably do a count too, but I'm not gonna make it too fancy right now. And then the equal symbol. We are not replacing anything, and the search is going to be a specific range, and the specific range is the entire column C. So to specify the entire column C, this is how you can specify the entire column C. I think that's all we need. Okay, so we can go for the next one. It's kind of cool. Okay, so this one we know already. This one we also know already. We know this one we know already. So when we go back to the stack here, this time we're gonna go like, okay, this is a 0, 3. Okay, 0, 3. This is now a 0, 2. And then we are repeating this several times. So the next one is gonna be a 0, 1. And then the next time it is a 0, 0. So the stack should go as low as these two locations. And obviously these will be repeated as well, like so. But I'm going to also color code these. Okay. We're gonna have to use, I guess, light red, berry free. Okay. And then we wrap around the color spectrum back to this side. There we go. Okay. So the point is we have four invocations of F. One, two, three, 4. Okay, so we should have four invocations of F. Each one has its own parameter n. Each one has its own return address. Okay, and we know the lowest location should be F6. So we now want to go back to the trace and make sure that that is correct. Okay, so I already know this is what is supposed to happen, but it always is helpful to really kind of visualize, kind of go to see exactly what is happening. So after the F6, I should not see any additional updates until we overwrite local variable x of main, which is at location FE, and that's exactly what happens. Okay, so this is the I think this is one of the most helpful way to visualize the way that we use the stack. Even though it does not look like it, looks like we have fragmented information kind of all over the trace. When you reassemble the fragments, then you can actually see the picture on the stack. Okay, are we doing okay so far with this exercise? Okay. So if I were you, okay, I would consider making a snapshot of the spreadsheet at this point, okay, because now the trace is all done. And once you make a snapshot of the trace, you can annotate it any way you want, okay. You can print it out, okay, on a piece of paper, okay, Control P, print it out, okay, and you can print it out, well, the way it is. No, that is not the way we want to do it. So when you want to print it out, I guess the best way is to download the PDF of a particular sheet, like the analysis sheet right now. Okay, we'll see. Okay, it's not the right orientation. Put it back in the portrait mode, and it is tiny right now. So we can change the font size and also make it change the formatting, show notes, over, center. Hmm. I don't know why it's choosing a tiny little font here. Oh, fit to width, that's why. So we'll change it back to fit to height, fit to normal. Okay, there we go. Ah, much better. Okay, but it doesn't show the line content, in this way. So you kind of have to play with this a little bit to see what is the best way to do it. Okay. But if you print it on the piece of paper, it means you can also bring it to the final exam. Okay, so there's a little plus of actually printing it out. You can also print out the source code if you want to, with your own annotations and whatnot on it. So kind of think about the final exam as you study. Okay, think about the final exam and go like, okay, what should I put on paper that can help me in the final exam? Are we good? All right. So I will leave this alone, okay, so that you guys have the time to kind of sign in, make a copy of this. Then you can do whatever you want with your copy. Um, cool. So now it's time to kind of give you guys the lab. The lab today is call frame. This is your lab today. The access code is framed. This one. I'll put it on the whiteboard. Framed. So, and you can start to do it as soon as I publish it, like now. There we go. All right. So based on what I saw yesterday on my Monday Wednesday class, this one does not seem to take too much time. Okay, and yet it's worth 12 points. So I think you may not need to use too much time in today's lab. All right. So I'll just double check to make sure you guys can get into the lab. It's not up yet. You can get into it. Okay, cool. All right. So once that is done, I am going to get some water to drink and then I'll be back to answer questions. But before that, let me stop the recorder. Up